Alright, so let's recall what we had done. We had started with the definition of vector space. Alright, so we had a notion of vector space. Then we went to subspace. Then we went to what is called a linear span. Then linear combination. The ideas were related here, and then there was a notion of linear independence. And dependence. So, we had learned all of them in some sense, fine. It is important to emphasize that I had not tried to prove anything as such to be a vector space. I just gave you examples. I did not verify the conditions which were required for checking whether something is a vector space or not. So, if you recall, to show that something is a vector space, what you needed was you have to define one vector addition, you have to define x plus y, you have to check that whatever you define it is inside that set itself, fine. Then that sum has to satisfy certain things, and what were they? They were associativity holds, commutativity holds, there is a 0 vector, and for every x there is a negative vector, fine. So, those properties were required. Then there was a scalar multiplication that had to be checked, alright. So, you have to define one alpha times x, and that should be inside the set. You have to also check that 1 times x is x, and then distributivity holds. So, there are a lot of things that needs to be proven if you want to prove that something is a vector space. To prove that something is a vector subspace, you need less work. What you are supposed to do is you have to say that, so I am saying that W is a subspace, alright. We need to show that W is a subset of V, where V is a vector space. So, I just have to point out, I just have to say that W is a subset of some set, fine. Also, W has to be non-empty, and what we need to do is that take any U and V belonging to W. We should be able to show from here that this should imply that alpha U plus beta V should belong to W for all alpha beta belonging to F, all right. So, to show that something is a subspace, I just have to point out, that this is a subset of something and it is non-empty, and then just do only one thing, which is show that linear combination is there in the set, nothing more than that. Is that okay? So, that way it saves our lot of time. Now, let us look at something about independence dependence. I had said it about the rank of a matrix. So, let me get into that with an example, so that you can recapitulate these ideas which are important. So, theorem. So, let A be an M cross N matrix with rank of A is equal to M, all right, sorry, rank of A is equal to R, then any collection of R plus 1 rows of A are linearly dependent. Similarly, any collection of R plus 1 columns of A are linearly dependent, all right. So, this statement is true in general. I will just give you a glimpse of the first part, because for the second part the idea is similar, but you are not used to till now looking at column transformation. That is one thing. The other thing is that I have not yet proven to you that row rank is same as the column rank, and hence I am not getting into that part. Fine. So, let me just say, and then after some time you can see yourself that you will be able to prove it yourself. So, I will not get into it, but I will try to prove the first part about the rows. So, let me look at the proof. Fine. So, what we know is that the rank is R. So, rank is R implies there exists an invertible matrix P such that P times A has the type B0, where this is R cross N, all right. Or what I am saying is that I am looking at the Gauss elimination method, or I can say that I am looking at the RREF of A, whatever you want to say, all right. You can think of this as P of A being the RREF, whatever what you want to look at, I can think of this. Once I have looked at it, what I see is that there are only R rows here, only R pivots. Fine. Since there are pivots, what happens to the pivots? These pivots, they will give me I sub R into play, and this will imply that these rows are linearly independent. Why will they be linearly independent? So, let us try to prove it. So, suppose I have the rows. So, I have got P of A, which is RREF of A. It has, so let me write this matrix as R in short. So, R looks like something here, I have a pivot here, I have a pivot somewhere here, I have a pivot somewhere here, and I have these pivots, R of them, and then there is a 0 here, and there is something here. Fine. Is that okay? So, now I am supposed to look at these vectors, all right. So, vectors are R of, this is my first vector, this is my second vector, and this is my rth vector. Fine. I am supposed to look at alpha 1, alpha 2, alpha r of 0. I want to solve this system, with alpha i's as unknowns. Fine. I want to solve this system. So, now if I look at, important, please note this here, that I am trying to solve this system. I want to show that each alpha I is 0. Fine. So, if I look at this part, this column, all right, I know that in this column, all other entries except the pivot is 0, all right. So, if I look at here alpha 1 times this, alpha 2 times this, and look at the corresponding entry here, corresponding to this entry, whatever this entry is, fine. I will get only alpha 1 here. Is that okay? So, I will have something here, I do not know, it has appeared somewhere. Similarly, this has come at some place, I do not know which place it is. So, this will give me again alpha 1 times 0, alpha 2 times 1, alpha 3 times 0, and so on. So, it will give me alpha 2 somewhere, similarly alpha 3 somewhere, and so on till alpha r, and then it will be, I do not know what is here. So, I do not know what these parts are. Is that okay? So, this is this multiplication is basically giving me this vector, all right, and we are saying that this vector is 0, 0, 0 here. So, this part will imply that alpha 1 is 0, alpha 2 is 0, alpha r is 0. So, therefore, I get that this is the only solution, fine. Again, so again note it down, I am looking at the RREF of A. Once I am looking at the RREF of A, I know that there is a ladder like thing coming into play. Since there is a ladder like thing coming into play, these ones are appearing at different stages, that is the one thing. Every other entry on those pivots are 0. Since every other entry in that pivot is 0, so what happens, alpha 1 times the first row and look at this part, alpha 1 times the first row will give me alpha 1 in this entry. All the entries here will be, since every entry here is 0, so alpha times 0, alpha 3 times 0, alpha r will give me 0 here. So, I will be left out with only alpha 1. Similarly, if I look at here, it will be alpha 1 times 0 is here already because it is an RREF. It will be alpha 2 times 1, alpha 3 times 0, alpha 4 times 0. So, it will give me alpha 2. Again, this is a pivot, so every other entry here is 0, fine. So, I will get only alpha 3 and so on. So, now I equate the two sides, I will get that alpha 1 is 0, all right. So, I will get this is the only solution. We have seen that if I look at A, which was of rank R, then we had this P times A is a matrix B with 0, and this matrix has size R cross n. So, cross n, and we are looking at this rank is R, and P is your invertible matrix, fine, and shown the rows of A, rows of B are linearly independent, right. So, now we need to show any collection of R plus 1 rows of A are linearly dependent, any R plus 1. So, we will just look at the first R plus 1. So, look at the first R plus 1 rows of A, fine. So, I am writing A as some A1, A2, and A1 consists of, this is of size R cross 1 plus n, and this is of size m minus R plus 1 cross n. I also have A times A is equal to P inverse of B0. So, we decompose B, decompose P inverse accordingly. Accordingly means the matrix product makes sense. So, I write here A1, A2 as something here B0. So, I can write it as some P11, P12, P21, P22. Now, what is the size of P11? It has to be defined so that I can multiply I can do the matrix multiplication. So, if I do the matrix multiplication, I can look at it as this times B, and this is P21 times B, the rest part is 0. So, this is going to be the size P11 cross B according to this part. If I look at this part, this is going to be of the size R plus 1 cross B. B, the size of B is R cross n. So, therefore, R has to cancel. So, I get R here cross R cross n. So, this will imply that P11B has size R plus 1 cross n, the size of A1. Fine. So, the matrix product makes sense. So, what we see here is the size of P11, is R plus 1 cross R. Fine. So, now let us look at the system. All right. So, consider the system. P11 transpose of X is equal to 0. Fine. So, now if I look at P11 transpose, this is a matrix of size R cross R plus 1. Since this is of size R cross R plus 1, so this system, the system P11 transpose of X is equal to 0 has a non-trivial solution. Why it has a non-trivial solution? Why non-trivial? Basically because P11 transpose, this is of size R cross R plus 1, implies rank of P11 transpose is less than equal to R, and the number of unknowns is R plus 1. So, therefore, at least one free variable implies a non-trivial solution. Fine. So, let x naught be a solution. So, let x naught be a non-trivial solution. This implies, we are looking at x naught, implies that P11 transpose x naught is 0. Fine. And we have x naught is not equal to 0. Fine. So, let us go back to the question. So, let us go back here. So, we need to look at A11. Fine. In place of A11, we are looking P11 transpose, basically because A11 for us is this. Sorry, A1 is this. So, this is what our A1 is. A1 is this. Fine. So, let us look at what is A1 transpose. So, let us look at. So, A1 transpose, if I look at, it is P11B whole transpose, which is B transpose P11 transpose, and therefore, A11 transpose x naught is B transpose P11 transpose x naught, which is B transpose P11 transpose x naught by associativity, which is B transpose 0, which is 0. All right. So, this implies we see that the columns of A1 transpose, which are R plus 1 in number, which are R plus 1 in number, are linearly dependent. So, columns of A transpose are linearly dependent if and only if rows of A1 are linearly dependent, and this implies what we are saying is that the first R plus 1 rows of A are linearly dependent. All right. So, we have shown that if I am taking the first R plus 1 rows of A1, if I am looking at the first R plus 1 rows of A1 here, all right, then they are linearly dependent. We can do the same for any row. Fine. A similar argument has to go through. The problem will be how do I interchange rows and so on. So, that will come through the permutation matrix, but the same idea will tell you that things will be nice basically because of this matrix P11 that I get will have this property that it will be of size R plus 1 cross R. All right. I will not get into the column part, as I said. I will just want you to understand it that similar thing can be done, but I have to define what is called the column rank. I have not yet done it. I have not related the two ideas, but at least you can show some things using the idea that A times Q will look like something here and then 0 here if rank of A is R, which is less than n. All right, there will be some zeros which will come into play, and you can use those ideas to prove yourself. Fine. I will not get into that part. Try that out yourself. Now, some very important results. All right, very important results. So, now I will come back to some results on linear independence dependence. So, the first thing that we had learned was 0 vector cannot belong to any linearly independent set. 2, S is linearly independent implies every subset S is linearly independent. 3, S is linearly dependent implies every superset of S is linearly dependent. Fine. We had all learned this. So, now the most important theorem, very important theorem. Let me write it. So, let S be a linearly independent subset of a vector space V over F, vector space V over F. Fine. then for any V belonging to V, look at, so I already have S as linearly independent, I want to look at S union V. Is that okay? This V could be in the linear span of S, it could be outside, it could be element of S itself, it could be anything. So, I am looking at any V belonging to V, then for any V, this is linearly independent if and only if V does not belong to linear span of S. Is that okay? Fine. So, let me write not V, let me write U here. I think there is a problem with these notations, I think, as usual. So, U here, fine, U here. Is that okay? So, what I am saying is that let S be a linearly independent subset of a vector space V over F. Then for any U, U could be either in S, U could be in linear span of S and things like that, it could be anywhere. Then we are saying that S union U is linearly independent if and only if U does not belong to linear span. So, what we are trying to do is that I have a linearly independent set, I want to increase the size of the linear independent set. I am adding extra vectors, I am trying to see whether what the new set I am getting it is that set linearly independent or not. Fine. The idea being very simple, that I start with a single vector, alright, which is the non-zero vector. Then we have already seen that the single vector which is non-zero is linearly independent. I want to add another linearly independent vector to, I want to add a vector so that the new set having two elements is linearly independent. What it tells me, this theorem tells me that you have to only choose those vectors which do not belong to the linear span. Fine, that is very important. Fine. So, let me prove it for you, proof. So, let S union U be linearly independent to show U does not belong to linear span of S. Fine. So, if U belongs to linear span of S implies U is equal to alpha 1 U1 plus alpha 2 U2 plus alpha k UK for some U1 U2 UK belonging to S and alpha 1 alpha 2 alpha k belonging to F. Fine. So, this implies I am writing it as this implies. So, rewrite this as 1 times U plus minus alpha 1 times U1 plus minus alpha 2 times U2 plus minus alpha k times UK is 0. So, I am rewriting the previous part as this. I have just rewritten it. Fine, that is all I have done. Now, if I look at this, it tells me that the system, it tells me that look at the system here, C1U plus C2U1 plus C3U2 plus Ck plus 1 UK is 0. Look at this system, or let me write it, I think. So, what we are saying is that look at the system, say C times U plus C1 U1 plus C2 U2 plus Ck UK is equal to 0. In the unknowns C, C1, C2, Ck, look at this system. In the unknowns this system has a non-trivial solution given by C is equal to 1, C1 is equal to minus alpha 1, C2 is equal to minus alpha 2, Ck is equal to minus alpha k. So, I do not know whether alpha 1, alpha 2, alpha k are non-zero or not, but I know that at least C is not 0. Fine. So, therefore, I have a non-trivial solution. Since the system has a non-trivial solution, implies that the set U, U1, U2, UK is linearly dependent. Fine. Now, this is a subset of S union U. So, you are saying that this set is linearly dependent, this is a superset of this set T, superset of T, and therefore, what you are saying is that there is a linearly independent set which contains a linearly dependent set. That is a contradiction. A contradiction to our assumption that S union U is linearly independent. Look at this, this is what our assumption was. We assumed that let this be linearly independent. All right. So, we had assumed that our set S union U is linearly independent. S was linearly independent. We assumed that S union U is linearly independent, and from there we wanted to show that U does not belong to the linear span. On the contrary, we have assumed here. We are assuming that U is in the linear span and then get a contradiction. The contradiction is to the fact that U is in the linear span. Is that okay? So, therefore, we have shown that if S union U is linearly independent, then U cannot belong to the linear span of S. Now, let us prove the other way around. So, assume U does not belong to linear span of S. To show U union, so this union S is linearly independent. So, be careful here, you already know. So, a starting point, the first assumption that we have is first assumption was that S is linearly independent. That is very important. All right. So, we are assuming now that U does not belong to the linear span. We want to show that this set is linearly independent. So, let us consider. So, if I want to show that something is linearly independent, I need to consider a system of equations. So, consider the system C times U plus C1 U1 plus C2 U2 plus CK UK is equal to 0, where UI belongs to S and C1 till CK are unknowns. Fine. Is that okay? So, we are trying to solve a system here where U is the one that I am looking at, and I have got collection of vectors U1, U2, UK from S, any collection. All right. It is not only just a few of them, I can take any collection, but this collection is finite collection. Is that okay? And I want to solve this system. What we are saying here is that this has the unique solution, C is 0, C1 is 0, C2 is 0. I want to prove that. To prove the above system has only the trivial solution. All right. Fine. So, claim 1, C is not equal to 0. Fine. So, if C is equal to 0, this will imply that we are looking at the system C1 U1 plus C2 U2 plus CK UK is equal to 0. We are looking at this system. All right. So, if C is 0, I am looking at this system, and I know S is linearly independent and UI belong to S. So, implies the only solution of this is the implies this system star has only the trivial solution. Fine. So, if I am assuming that C is 0, then this whole system has only the trivial solution. Fine. Because C is 0 and this part is also 0. So, this part will have a non-trivial solution. So, now therefore, we have shown that claim holds. Fine. So, again let us understand this very important idea that I have looked at a condition here, a system of equations where we have to show that each Ci and C is 0. So, the first thing we are assuming that C is not 0, we want to claim that. So, if C is 0, then there is a problem here that we can see that if C is 0, then we are solving a system of equation where the vectors are coming from S, and those vectors are already linearly independent, so that gives me a trivial solution which is 0, 0, 0. So, if C is 0, everything is 0, all the Ci's are 0, alright. Now, if C is not 0, then what happens? I can write U as 1 upon C times C1 U1 plus C2 U2 plus Ck Uk, alright. So, I can write U in terms of linear combination. So, this belongs to the linear span of U1 to Uk, which is a subset of linear span of S, fine. So, if C is not 0, then I can write U as a linear combination of elements of U1 to Uk, and therefore, I will get that that belongs to the, so U belongs to linear span of S, and that is a contradiction to our assumption that U was not in the linear span, alright. So, that finishes this lecture here. I want you to understand that this is a very, very important theorem where we have said that how to go from a linearly independent set to the next linearly independent set and so on. How do we expand the size of the linearly independent set, alright. That is all. Thank you.